So let's go. So the first part was easy. Everything compiled. But now I'd like to bring you to the world of CompletableFuture. But this talk won't be about basics. It will be about interesting parts. Those unintuitive or just simply weird. So CompletableFuture is one of the basic primitives when it comes to working with asynchronous programming in Java. But unfortunately, as I hope you will see with your own eyes today, there's quite a lot of interesting twists that you probably wouldn't discover. That you'll probably discover only on production, just like I did. So I'll try to do some live coding today, but I'm an architect, so I'm not sure if that will work. I mean, it worked on PowerPoint, so let's see if that works now. And let's go forward. So synchronicity is beautiful, simple, and trivial. We have two processes. Process A starts, it ends, process only then process B starts and then ends. Simple, easy, bulletproof, and terribly inefficient and slow. Because imagine how slow our computers would be if they were running only one thing at a time. So there is a need for asynchrony, because this pretty much allows our systems to get faster and more efficient. And asynchrony means that those two processes can start at the same time. One can start earlier, second later. We really don't control when they stop and what they return. There's no synchronization, which means that there's no synchronization between them. And suddenly, simple things become difficult, because let's say you want to run those two operations in parallel, asynchronous. Suddenly, it's very difficult to how do I return how do I even get that value back, right? I made this operation compute on a side, and it's computed, but I don't have the value. How do I get it? And this is where the concept of future or promises come into place. So it's a wrapper holding a value inside. You can think about it like an optional, but with this temporal aspect. So it's a place where a result of an asynchronous computation will eventually appear. So the state of a future changes over time. Usually at the beginning of its life cycle, it's empty, but at some point in the future, the value appears. And the good part is that any method can actually become async. This is not a property of a method. This is something that we control. So if you have a synchronous method and you want to run it asynchronously, you take this method, run it through your custom executor on the thread, and bam, it's suddenly asynchronous. And in Java, we've had two main implementations of future. There is CompletableFuture and standard future. Future is an interface, but usually when we mean future, we mean one particular implementation. And the original future has issues. Let me show you how it works. So in order to create something asynchronously, we'll need to have some thread pool where we can run it, submit, and we did the return. Let's return something here so that we get an integer. And now, if you have a look at the API, we have a couple of methods. Just ignore the red ones; those are fairly new ones. You can get, well, as the name suggests, you can just block and wait for the result. You can cancel. So if the operation's been running for way too long, and for some reason you decide you don't want it to be running, you just call .cancel. You can make a get with a timeout, so you don't want to wait infinitely, but for some time. And then you can check if it's done or cancelled. And that's literally the whole API of classic future. And this is kind of limiting, because if you start thinking about cool things that you want to do with parallel computing, it's really hard to find something that supports that. So imagine a scenario: you are implementing your own Forex broker, and you really care about obtaining currency exchange rates as fast as possible, at least with reliable latency. So in order to ensure reliability, you issue 3 calls in parallel to, let's say, 3 different currency exchange providers, and you always return the first one that was returned, that came first. But suddenly, how do you do that if you have just a couple of options on your future, like a get, cancel, and is cancelled? Well, it's not rocket science, because if you control the place where you create that operation, you can figure out, oh, perhaps instead of returning a future, I should be pushing those results into a queue and then wait on that queue for the result to happen. So yeah, that's not rocket science, but again, that introduces a lot of extra complexity. And let's say I would like to do something like, so once this operation completes, just print it out. And if you start thinking about classic future, this is way harder than it could be. So the blocking API is somehow limiting, because naturally when we run asynchrony, we would like to be able to do something in non-blocking way. Exception handling capabilities are kind of limited, because if you call .get, you get to pretty much do a big try-catch with a couple of exception types, and that's all. And a future can't be manually completed. So in most cases, when you obtain a future, you don't have any control over what's happening with it. It will just eventually, you need to trust that at some point it will eventually complete. And this is problematic, because there are use cases where this actually is very much needed. But one of the biggest problems is that multiple futures can't be really combined in a natural way. So just like with that example with Forex exchange, whenever you need to figure out, when you are, for example, waiting for we have two parallel requests, and you're waiting for the first one to complete, and suddenly when you start coding that out, that's slow, boring, and error-prone. Not rocket science, but still you can make a lot of mistakes and still distracts you from the job that you want to do. So that's where, before JDK 8, the solution came, which is Google Guava and Listenable Future, which was a bit better, because you could already register listeners on your own future instances. It was ugly as hell, because before JDK 8, lambda expressions used to look like that. Well, no one would call them lambda expressions, but they serve the same purpose. They were terrible ugly. This got improved in JDK 8 with CompletableFuture. And as the name suggests, the future can't be completed manually. So future is no longer tied to an underlying operation. There is no one-to-one mapping between a thread that's executing an operation and the future that holds the value. It's just a holder with a value that you can complete by yourself, or can never complete. Or perhaps there can be multiple threads that complete it. You never know. So it's perfectly reasonable to go for something like new completable future, and, for example, call join. Well, maybe it's not perfectly reasonable, because what we are getting here is a permanent deadlock, because obviously no thread will jump in and complete that. But suddenly operations like figuring out, like when you receive completable future and you need to update this value and introduce some simple race, suddenly it's possible, because it wasn't with the classic future. But most importantly, completable future allowed very easy declarative approach to combining computations. Because besides simple boring .get, you get to then apply, then combine, then run, and all of those various API methods that actually return other computable futures. So to give you an example, the API of the CompletableFuture is very, very rich. I would actually say it's a bit too rich because you can get easily lost in all of those methods. But the cool part is that most important ones are here that were not in the standard future. So let's say I want to process that result that arrived in that future asynchronously. I can go and say, let's make it an integer. Let's say f plus 1. And my return value is a CompletableFuture of integer, indicating that this value is computed asynchronously. This is powerful, this is easy, way easier. And then combining two futures, suddenly it's super easy. You don't need to think, oh, I better, instead of creating futures, create a blocking queue and put stuff in there. But instead, you write it declaratively. Super easy. But this talk is not about the basics. There's a guy that does it better, Java champion, that wrote a book about reactive programming, Tomasz Norkiewicz. You probably should watch this one. But even if you're not familiar with the basics, you should be able to learn quite a lot during this particular session. And we'll start with very basic, very common issue. Cancellations of completable futures. And this is quite a common issue. So the main problem is that original future and CompletableFuture, they share the same interface and the same methods. And in the past, if you go over executors and you want to execute something in there, if you start digging deeper into actual implementations, let's say, not fork join pull, but if you start digging deeper, you will somewhere in there find an information about something like runnable future. So it's this interesting interface that combines runnable and a future, essentially indicating that this is both. This is something that runs, and this is something that also returns a value. There was always this one-to-one mapping, but that's not the case with computable futures. That's why people are quite often surprised when they go to the CompletableFuture, they schedule some operation, they do cancel, and they think that they've canceled the underlying operation. But that's not really the case, because if you have a look at the documentation, it's quite openly stated that parameter may interrupt if running. This value has no effect in this implementation because interrupts are not used to control processing. And this is quite often a source of surprise because people are surprised that, well, I canceled my future. I got an exception, cancellation exception, but it's not canceled. How could that be? And the reason is because it's not really possible. Because if you go back to this original example and start thinking, so there's the original future, and then we called then apply. We augmented the original future with the simple incrementation, but that returned another future. We then combined and then run. So what should we do if we cancel the last one? Should we cancel only this small piece of computation that should be run here? Or should we propagate the cancellation to the very top? But what if a future is completed by multiple threads? Should we interrupt all of them? All possible threads that could have completed the future. And suddenly, when you don't have this one-to-one mapping, this becomes inherently a complex issue, actually unsolvable. Because as long as you are not tracking all the potential threads that could have completed it, there is no way to solve it. And that's one of the main, things that you need to remember about. Because unfortunately, I don't really have a very good solution for this one. Sometimes, if you control both options, if you control the side that creates a future and the side that accepts it, then it's okay to do kind of a hacking where you can start manually controlling the original tasks that are supposed to complete the future. But in most cases, that's not okay and that's not really safe. But so you can hack it out, but in most cases you probably shouldn't. I can do that because I wrote a part of the library where I fully control what gets both sides, both the sides that submits a task and both that receives one. But in most cases, there's no way. And if you are working with pure computable futures, you need to accept the fact that you can't cancel operation. If you're after cancellations, you probably should start with the original approach and then perhaps piggyback on top of computable futures when you need them. So that's one of the basics. First, like limitations of the future that you need to be aware of. That's being able to conveniently complete futures is a trade-off. So we need to forget, unfortunately, we need to forget about cancellations. But here, let's start inspecting some of the interesting parts of the API. I mentioned that future is great because suddenly it's now easy to combine and do nice stuff on multiple futures. So let's see how it goes. So let's create an executor. Let's say anytime random number of threads in there. Let's help ourselves with a helper method, public static void integer process. Let's make it int value. No, void integer, right? Architect writing code. So thread slip. And just return. Yep. That's as complex as it gets. So once we can simulate some simple processing, let's now try to create a couple of operations. CompletableFuture, supply async, and supply process, let's say 1, and then CF1, and let's do CF2. Okay, so we have 2 futures running, and did I do it right? Or didn't I forget about something? What do you think? So we are trying to run those 2 futures, those 2 operations on that executor service. Did I miss something or not? How does this class know that it's supposed to run on this executor? It doesn't. Okay, I missed and didn't provide one very important parameter here, and this is absolutely crucial to understand how harmful this API can be. But we'll circle back to this in a second. So we have 2 futures that return, let's say, values with delay. So let's say we want to wait for all of those values to complete and receive results. So you browse through the API and you find a method like all_off, which sounds like exactly what you need. As you can see, it accepts var args of futures. So we go CF1, CF2. Okay, it looks like done. And it should return a computable future with results, right? Okay, and okay, this is weird, because what we got is computable future with a void inside. That's weird, right? Because we use all_off. I provided 2 futures. We are waiting for all those futures to finish and complete, but we are getting a void on the result side. Perhaps I messed something up with the coding. No, it looks like this method permanently, always, and on purpose returns a void. So the reason it's like this, it's designed to be used as a signaler. So it signals when all the futures have completed. But it still could be a bit easier, right? It would be a bit more convenient if we are waiting for all the futures, we still could have the list of results inside. Would be a bit more convenient. But if you start looking at this method for a bit longer, you start noticing more weird things, especially this wildcard there. So why would you wait for futures of different types? I mean, I can imagine scenarios like that, but How often do you do that? In most cases, when you want to wait for futures, those are futures returning values of the same type. How often do you wait for a future that returns string, car, person, and something else? It can happen, but it's a rather uncommon scenario. And even whenever you need to do that, you could still assume that you're working with object and not any particular type. So API looks weird, but it's not everything. Let's see how it works. So here we are starting those two operations. We are waiting for them. So let's go result, join. We run it. We wait around a second. And nothing happens. And this happens precisely because I've forgotten to shut down the executor service. And as you know, JVM will stop only if all non-daemon threads have completed. But we still have threads in the pool. So let me shut it down for you. Oh, and as you can see, the process finished in around a second when all those operations completed. So in this case, now at this moment, we are sure that all futures are done and the results are ready to be processed. But imagine what would happen if we introduce exceptions into a picture. So let's say that particular one, it does some processing, but let's say after some time, it throws an exception. So as you can imagine, probably in this future will never properly complete. I mean, it will complete, but it will propagate an exception further, right? So let's see if that's the case. So we are running, and we got the exception as expected. Everything looks fine so far. API is weird, but works. But now let's imagine a scenario that we have a very long processing here. Let's make it very long. So how would you expect this to behave when I run it? We have two futures, out of which one completes immediately with an exception, and second one waits for a very long time. Who thinks this should complete immediately with an exception? Please raise your hand. People. Who thinks that this will complete after a very, very long time? Okay, nice. But see, I still see quite many people that didn't raise their hands, which means that we need to calibrate the room first. So, because it's really hard to derive any reasonable data from the fact that we're seeing that many people didn't raise their hands. So, please tell me, answer one more question. Who is in this room? Okay, now it makes a bit more sense. So, we've introduced this very long waiting time. We run it. And we are waiting. Because for some reason, OAuth is not waiting for successful completions, but it's waiting for completions. So, although it might encourage you to think that that's really the case, that if there is no way for all of those futures to complete successfully, this exception should be propagated immediately, but it's not. And it's not rather a common scenario to actually wait for everything to complete, regardless of it's successful or exceptional, and then finish. And this is I've seen this in production. I've seen this in popular open source frameworks. So that's, for example, a snippet taken from test containers. And there's quite a lot of sophisticated coding in here, only then to do all of at the end, which essentially results in the fact that when you run, let's say, n containers from test containers, and one of them, let's say, due to misconfiguration, completes exceptionally immediately, you will still wait for all the other containers to complete, start up, and then exception is fired up, and they are killed off. Okay, waste of time. So this happens. Yeah, yes, I fixed that. There's a pull request. So as you can see, now we know what can we do. We are aware of the problem. So now let's try to fix it. And this is which we'll see right now is quite a common way of working with more advanced cases with CompletableFuture. Because in original future, there's nothing you can do, but in this one, you can introduce races. You can introduce races in multiple processes that fight to complete the future, and the first one that succeeds is the one that propagates the result further. So let's go over, let's copy-paste that piece of code. And let's try to think how would we fix the method signature. It would be nice to have it return something like a list of our T, right? Well, we don't have a T, so we need to introduce generics. And now, we would like to ensure that potentially all computable futures of the same type are here. Var args is not super convenient, so let's maybe make it a list. All of, and make it short-circuiting. So we have a list, CFS, and what do we do with that? So first things first, all of method is not garbage, it's still pretty useful. And if you have a look at the inside, it's pretty smart. Because what it does internally, it constructs a pretty smart completion tree. So those signals are propagated pretty optimally. So let's try to use that. Because what we'd like to have all of semantics with short circuiting, and a bit different, simpler API. So let's try to use that. CompletableFuture, all of, and now probably the most difficult part: how to convert a list into an array. CFS to array, new CompletableFuture. Okay, it's so funny. So tell me what's the proper value for the array to be initialized with. You will probably say, oh, we know the size of a list, we know the size of an array, so we do CFA's size, right? Makes sense? No? Yeah, please. No, it's not -1. So this is an example of a bad API design. Because there's actual good answer to that problem, but we are burdening the developer with making the choice, although we could have made it ourselves. So actually the answer is 0. So you might think, so both are correct. Both are correct, will give you correct answers, but if you pre-initialize the array, that you send it to array method with a size, JVM will spend actually quite a lot of time zeroing all those elements. And then overwriting them with elements from a list. But if you start from 0, this process is completely avoided, which means it's faster. If you want to read more about that, if you start Googling, you will find Alexei Shiplev's article, and he explains it in 60 pages of assembly code, pretty much. So, but, by the way, the cool part about the newer Java versions is that they actually introduce the API that don't burden you with making a choice. So there is a new toArray method which accepts a function where you can say CompletableFuture array and point to a constructor, and this is enough. Because underneath it, when you provide the function and instruction how to create an array from having an int, this internally can be handled, and it's available since JDK 11. But I don't have JDK 11 here, so let's go with the 0. So we have our result with void. But we would like it to have inside actual values from here. So we know that if this future completes, we have a guarantee that all of those have already completed. So the trick that we can use is that we can go result, then apply, and in here we need to say what to do with that void. Well, void is a null, it's useless. We can just ignore that. We ignore that. Once we are here, we already know that future is, all those futures are completed. So we can go forward and simply stream for all of the futures and convert them into actual values, because we know that join will not block, but actually just return all the values. And that's pretty much it. We are just missing one very important part, the short circuiting. Because now if we replace all of with all of short circuit here, it will work, and list integer, it will work just like the original Olaf, but having a new, let's say, a new wrapper on top of that. So in order to introduce short-circuiting, we need to introduce a race, which means we need to have another process that will try to complete that original result with an exception as soon as it appears. And there's a very easy and declarative way of doing that, because we can simply for each say that for every computable future in that original list, when it completes with an exception, which means we need to check if throwable is not null, complete our result, complete exceptionally our result with that throwable. And we introduced a safe race. By the way, it's safe according to Java memory model. So if you would like to check that, I've done it already. So let's run it. And our short-circuiting is there already. Luckily, you probably won't need to rewrite this code each time you need to use that. It's easy. All the alternatives of that are easy to find online. But as you can see, unfortunately, we need to spend quite a lot of time to address a very basic use case, which is not supported by CompletableFuture API. The same kind of problem appears with any of, but slightly different. So let's go back to this original case here. Let's roll it back, return process2, and instead of all of short circuit, go for something like CompletableFuture, any of CF1, CF2. So any of, as the name suggests, it returns the value of the future that completed first. But you can already see that it might be a bit inconsistent because it returns an object and previous one didn't. Okay, that's weird. So it accepts futures of different types and returns an object, forcing you to pretty much do an instance of checks if you really want to process futures of different types, which is suboptimal, I would say. But it also behaves in a weird way. So we have two futures in here, returning 1 and 2. Let's quickly go for then accept, provide something like that, so that we can see what value is inside that future, and join and wait. What's going on? All right, we are waiting for a very, very long time. Forgot about that. Let's run it again. And after a second, you see that value 2 was returned first. Technically, well, we are waiting the same. We are waiting only 1 second, so technically this can be either 1 or 2. But it works as expected. If we introduce some, let's say, if we return 2 directly without waiting for that, I would expect 2 to always return first. If we change it to something else, this should pop up first because that's the one that completes first. Okay, great. But what if we introduce exceptions into a picture? So let's say we call that process over here. We wait process. Let's give it the result. Oh, actually, we don't need the result. We just throw an exception after some time. And there is value process 2. So since the first one is completing after some time and with an exception, when we run it, we would always get value 2 returned after a second. That's natural. But what if this takes 1 second to return and we remove that process from here? If we run it, you will see that any of completes with an exception first. So we have 2 operations. First one completes with an exception immediately, second one after a second. And any of won't wait for the first successful completion. It will return first that completed, irregardless of the fact if it was successful or not, which again might be pretty unintuitive. And people usually are surprised when they figure out this is indeed the case. And again, I can understand, I can see some value in that, but the fact that they introduced an object into here, I think is inconsistent with the design of both methods, because I would expect to have a void in here and it would be more or less okay. The solution to that looks pretty much like this. So unfortunately, you still need to handle everything by yourself. But in this case, you can't really piggyback on top of any of method because it returns exceptions first. So in this case, you need to create the future manually, then write your completion logic manually as well, which is pretty easy. You just iterate for all the futures, you call then apply, and when this future finishes, you just complete the original one. And then you just need to remember about this corner case that perhaps all the futures failed. And if all the futures failed, then complete it eventually with an exception, if there was not even a single positive completion. So we've discussed only cancellations and two different popular methods which worked in a hopefully surprisingly, I mean, unfortunately in this way, but hopefully, because I hope you didn't know about that. But now let's go to the most interesting part, CompletableFuture and threading behind that. And you've seen a small, tiny piece of that already. At the beginning, when I started writing code, I forgot to include the executor service right in here. But it still would compile. So the question is, where would that code actually be running? Let's check that. In order to check that, well, we don't need that code anymore. In order to check that, let's introduce something here. Thread, current thread, get name, so. And now we can see where it actually gets executed. We need this. And we need to replace that with a process 1. So as you can see, this is actually executed on a thread pool taken on threads taken from this particular thread pool. If I would like to really prove it to you, I would need to create my own thread factory and override the name. But you can trust me, this is this one. But the question is, what happens if we remove that? Because API clearly allows to do that. And this is Java 8. This is before the Project Loom times. Where would that run? Because there are a few options, right? Technically, it could just create a thread on the spot. It could use some shared thread pool. It could create a thread pool on the spot. It could run it in the cloud. I don't know, right? So it needs to be one of those couple of options. Let's run it and see. Right, I forgot to join on them. And CF2. So as you can see, it's fork join pool, common pool, worker 1, worker 2. So it turns out that there is a very special pool available in JVM since JDK 1.7. It's called fork join pool. So it's an experimental pool which is fine-tuned for operations that are CPU intensive. Its design is a bit different from standard thread pools. Standard thread pool is just a big bag of threads and a big queue in front of that. The problem with that is when you get a lot of threads in that bag and a lot of producers putting stuff into that queue, you will get quite a lot of contention because you end up with something called multi-producer, multi-consumer queue. And if there are so many consumers trying to read it at the same time and so many trying to put there, well, there will be a lot of time lost on synchronization. So in order to avoid this kind of concurrency performance issues, they designed the fork-join pool. A pool that had, instead of a bag of threads, there were just a handful of threads which correlated with the number, usually were supposed to be correlated with the number of CPUs on your machine, and each of those threads would have its own queue in front of that. If there is just one queue in front of each thread, there is limited number of limited contention that's happening. And if one particular thread runs out of tasks, it could steal a task from a queue of another thread. And thanks to this, using just a handful of threads, you could squeeze a bit more performance because those threads wouldn't be busy waiting for tasks to be delivered from the main queue. And the reason it exists like that, it was originally supposed to be used mostly for CPU-intensive jobs. So you have, let's imagine you have n core, you have 4, 5, or 8 cores on your system. You end up with 8 threads, 8 queues, and just like with what I told you about Hazelcast at the beginning and this thread per core idea, there is limited number of synchronization. You don't need to waste time on synchronization I mean, there is synchronization, but less than it would be with the multi-producer, multi-consumer queue. With this architecture of this thread pool, we are getting as close as it gets to the bare metal performance. But the condition is that you have a couple of threads which are correlated with the number of your cores on your system, and they are doing work that's CPU intensive. So the question for you is, did we do a CPU intensive work here? I will remind you. Is this code CPU intensive? Not really, right? Because what's blocking? The thread goes to sleep, and that's pretty much it. So the thread is, so cores are effectively busy sleeping, which is probably not a very efficient way of utilizing a core. So if we have this thread pool, which has a limited number of threads, which is fully dedicated to CPU-intensive work, imagine like sorting, array processing, and stuff, and we throw there a job to wait and sleep, it's kind of a waste of potential resources, right? And it's very easy to end up in a situation like this, because the default supply async method, it schedules everything on a shared fork-join pool. And this is pretty tricky, because if you have quite a lot of code like that, your fork-join pool that's supposed to do hard stuff is busy doing nothing, mostly being blocked and sleeping, which can be very, very inefficient at times, because you might be thinking that you are running all those things asynchronously, but you only have, let's say, a limited number of threads in your thread pool. So if you have 8 threads in the fork-join pool, and you throw in that your jobs last 1 second, and they are all just sleeping, and if you throw 16 jobs into that thread pool, it means that you'll probably wait 2 seconds, not just 1 second for them. What's more, this thread pool is used as a default for parallel streams. So if you use parallel streams in Java, there's no way you can provide your own thread pool, but it uses fork-join pool. So if you are using fork-join pool streams now, and you supply extra jobs for a CompletableFuture that are blocking, you might be parallelizing your parallel streams and making them slower. That's also why it's probably a bad idea to go, command replace on the whole project stream with parallel stream. But it gets even worse, because you probably heard about Project Loom and virtual threads, an ability to create millions of virtual threads. But guess what? Who runs those virtual threads? Fork-join pool. Yeah, real cores on a fork-join pool. Because at the end of the day, there needs to be an operating system thread that's running the virtual threads. So if you're fork-join, I might be lying here a bit, because the Project Loom is evolving. If you pollute fork-join pool, technically you can be impacting the carrier threads that are supposed to execute your 10 millions of threads at the same time. So what's more, let's assume that you and your team are aware of all of that, and you are very cautious about what gets put into fork-join pool. But let's say you run in an enterprise setup, you have application server, and there are multiple and there are multiple applications being deployed there. But what are application servers? Those are one big JVMs, which use the dynamic class loading to wire up your applications, which means they have fork join pool, one shared for all. I'm not sure if all the application servers do, but some do. One fork join pool shared for all the applications running on a single application server. So if you are doing everything perfectly fine, there still might be another team that has their application built in a, let's say, without of sleeping in a fork join pool, and it will ruin your application as well. So this is a bit shady, and I would argue that defaulting to fork join pool is probably a controversial idea. But hey, you need to be aware that this is the case. So the proper solution here is always remember about adding that small that executor service parameter, so that we always control what we block. So it's perfectly fine. If you create a separate fork pool that's designed only for doing blocking operations, you can fully pollute it with whatever you want, and you still will be fine, as long as you don't touch the shared one. So that's perfectly fine. Okay, so let's do it. So we know that by default we go to fork join pool, but let's do a small experiment. Let's remove that code. We'll be using this executor service over there. We go supply async process 42 on that particular executor. There's this future f, and now we do like this. Then apply I plus 1. Then we go something else, and we have like this processing chain. And now a quick question to you. Who do you think runs those operations? They all return computable futures, but who runs them? And the natural intuitive answer is that probably the same thread that did execute that original process, right? So let's check that. Let's add here, for example, current thread, get name, sought, and return I plus 1. And that's indeed the case. So as you can see, if we chain those multiple operations, it will be the same thread. It will be the same thread to execute it as the original operation. However, there are corner cases. What if that operation completed before we even managed? Let's say there is something happening here. What if that original operation completed before we called then apply? Suddenly, this original thread is gone. It's no longer there to do the job. So what do you think should execute it? Because there is, again, a couple of options. So let's, instead of doing process 42, let's try to simulate that and just return 42 without any delay. So let's run it again, and let's see what actually will get to execute that code. It might not be visible on the first try, but it actually was. We got lucky. So as you can see, that operation completed immediately 42, but what we saw here is main. Main thread is the thread running the main public static void main method. So we are saying, wait, Greg, we called then apply. We got a CompletableFuture indicating that this operation is asynchronous, but it still got executed by the same thread that called it. Yes, that's the case. So imagine a scenario that you're writing this smart code, multiple futures, there is some blocking, then apply. And the original future, and in then apply, you run, let's say, very long and blocking operation. And there's a corner case in which it might turn out that although you got a future, you are still blocked. So it tricks you into thinking that this is asynchronous, but in most cases it is. But sometimes it isn't. It will just literally block the calling thread. And again, this can be surprising, and that's why there are multiple variants of the same method that exist. So when you have then apply that returns a future, well, it looks like it's an asynchronous operation. But actually, it could be a bit more asynchronous. That's why you get then apply async. So once you add async to then apply, then you still get a future. It looks the same. But now you have a guarantee that it will be asynchronous. So now, if we run it, let's see if this is the case. Let's run it. Hey. So I said it would be run asynchronous, but what happened here? We are back to fork join pull. So the default approach to then apply async and then something async is that if you don't provide an extra parameter, it will again trick you into throwing that stuff into the fork join pull, causing all the problems we've just spoken about. So as you can see, again, I would argue if that's a friendly and intuitive default thing to default to. The proper way of ensuring that this is always run on the asynchronously on the thread pool of your choice is, again, remember that there's one extra parameter at the end. And now you actually see that it's being executed on the pool of our choice, as it was designed to be. So as you can see, this can get pretty tricky pretty easily. But that's not all. Because now, remember in the previous talk we were discussing, how the world of containers and cloud changed things and the rules of the game. This is kind of the case. This is the kind of the case here. So it's quite often the issue that suddenly in the cloud we might be dealing with grandma's computer, right, with just one CPU. And if you try to Google that, try to search it on Stack Overflow, people constantly have problems because the runtime get runtime available processors method returned 1, which should never happen. What does it mean in practice? I actually did lie to you about what executors are used by default by CompletableFuture. Let's actually dig into that and find it. So look, if we don't provide an executor here, we jump to supply async method, and it has some static pool here. And this can be either a common pool, in case when this flag is set, and that flag is set pretty much when there is more than one returned by available processors method, which is normally the case, should be the case, but in the cloud quite often isn't. But if there is just one CPU and Java thinks that you are running on your grandma's computer, it abandons the idea to use common pool, and it uses a thread per task executor, which is implemented this way, which is just not really a thread pool, just it's spawning threads on demand. So if for some reason you have just one CPU, I mean, Java thinks you have one CPU, you won't be even using a thread pool, but just creating threads on the spot, which can behave in a weird way. And again, this is understandable, because if you start thinking, if we had a fork join pool with one CPU, it would be quite one thread. It would be quite easy to deadlock it. But in this case, I would probably argue that at least using cached thread pool would make a bit more sense than just creating threads on the spot. So as you can see, this is pretty interesting. But that's not all. And the last thing that I'd like to show you for today is apply to either and how it behaves with exceptions. By the way, this whole reason why that the problem with fork join pool is the reason why I created that library of mine, parallel collectors, which actually allows you to, well, the example was here, which allows you to use parallel streams, but with custom thread pools. And this is all managed by custom collector implementations, which can do it in parallel and return completable futures. I will be revising the library for Project Loom once it's out. It has like 500 stars now on GitHub. So, final thing to today. A very easy operation. Apply to either. Super easy. So imagine we have a CompletableFuture with CF1, let's say with integer, and CF2. Apply to either is a super easy method that allows you to apply a method to either the result of the first one or the second one. CF1, apply to either CF2, and we can provide a function. In this case, an identity function, but we don't want to do anything with that. We need to pass the value further. And you can see that if we go then accept and join, we will see nothing because that never completes. So go CF1 complete with 1 and CF2 complete with 2. Well, on the first try, we get 1 because, well, this can happen because it's applied to either. You say you don't care which one to apply to as long as it's successful. Run it again. It's 1. What if we don't complete the first one? We get 2, right? Makes sense. Nothing weird so far. Let's start playing with exceptions. So CF2, complete exceptionally, new runtime exception. We run it, and the value returned is 1. Everything looks normal so far, because, well, when we say apply to either, we have 2 values. Well, one completed exceptionally, but there is still a second available, so we get our values back. Okay, what if we switch now the order of that? What if the first one is to complete with 1? What if the first one is to complete exceptionally and second to complete with 2? And we got an exception. So despite the fact that we have perfectly valid value here, 2, ready to be returned here, we got completion exception with runtime exception propagated instead. If you understand how CompletableFutures work internally, it makes sense because it's the first feature that's driving the whole process and how signals are propagated further. But unfortunately, this results in a kind of undesired behavior that you can see here. And again, I've seen this a couple of times on production. People surprised. How come apply to either failed, although we had a perfectly valid value out there? So, for example, people could do like new CompletableFuture and just return the default here. And then, but it still fails. Because that's come to CompletableFuture, unfortunately, works. And that's pretty much all I wanted to share with you. So those 4 interesting parts about CompletableFuture, which is cancellations, the interesting parts about threading, any of, all of, and apply to either, and apply to either async, and so on. So this is not often talked about, but I hope you didn't know about those cases. So I hope you learned something new. If you have any questions or something, you can, I don't bite, so you can find me on Twitter, LinkedIn. There are around 60 people with my surname in the world, and there's mostly family, so it will be easy to find me if you really can't Google that up. So thank you very much, and hope to see you again.